Hello, I'm Shaull and I'll be talking about explainable multi-agent pathfinding. This is a joint work with Morteza Lahijanian from Colorado. Before we get to the explainable part, let me talk a bit about multi-agent pathfinding. So in multi-agent pathfinding, we are given a set of agents, in this case some warehouse robots, the green, red, yellow, and blue robots, in some environment, in this case the warehouse, and each agent has a target. And our goal in multi-agent pathfinding is to find a plan for the agents, such that when each agent follows their plan, they get to their target, and if they take their plans simultaneously, the agents don't collide. So for example, we can run these agents within Planner and find a plan for them, and they run about and reach their targets. Now suppose there is some human controller who needs to see a plan and decide whether to execute it or not. And we want to convince this human controller that the agents indeed don't collide when executing the plan. How can we do that? So one way is just to give out the video of these agents not colliding. And if you follow the video very closely, you can see that they don't collide, but it's quite hard to follow, especially if you have a lot of agents or if they run about very fast. So the standard way of presenting this kind of plans is to give out the set of paths that compose the plan. And the problem with this is that from this set of paths, you can't determine whether the agents collide or not because the paths themselves do intersect. And that's not a problem in general, but you can't tell if the agents collide or not because you don't know at which time point each agent reaches their target. So what we present in this work is an explanation scheme to convince a human controller that the agents indeed don't collide. And that involves a slightly different representation of the plan. And the way we do it is as follows. Instead of presenting the entire set of paths, we only present time intervals of the plan, such that within each time interval, the paths themselves are not only not colliding, but also disjoint. So for example, in this plan, if we take the first 9 time units and just present them, so at times 1 to 9, the red agent only followed this path, the green agent only followed this prefix of a path, and so on. And it's very easy to see that the paths are vertex disjoint. And if we take the second time segment, then again the paths themselves are disjoint, and a third time segment that completes the plan is also vertex disjoint. And what we do now is take the entire plan and just decompose it into these 3 frames. The first time segment, second time segment, and third time segment, and present these 3 images to the human controller. And the human controller can very easily see that the agents don't collide. Now I'll remark that this it's really easy to see that because finding out if 2 lines intersect visually happens very early in the cognitive process. So it's very easy to see that the lines actually don't intersect. Much easier than following, say, a video of the agents. So formally, what is this disjoint decomposition? Well, the input for multi-agent pathfinding is a graph, consists of vertices and edges, a list of sources for the agents, and a list of targets for the agents. A plan for the multi-agent pathfinding is a set of non-colliding paths for the agents. Now, given a plan of length, say, t, a disjoint decomposition of the plan is a partition of the times between 0 and t, such that within each interval, the paths themselves are vertex disjoint, as we saw in the previous example. So why do we need to explain these plans? Well, as we mentioned, there are some applications for this. For example, in warehouse robots and also in air traffic control, where the controllers of air traffic actually do it by directing each plane where to go with the human. So if the human sees a plan, they need to be very convinced that the plan actually works before they give the directions to the airplanes. And if we want to automate that, we need somehow to explain to the humans that the plans we devise are actually correct. There is also a strong relation, of course, to explainable AI, XAI. So in explainable AI, typically we try to explain all kinds of classifiers or plans that are devised by very complicated algorithms, a lot in learning and deep learning, where we don't actually understand why the controller does what it does, or why the plan acts the way it does. And the reason is that the algorithms are really, really complex. And what we should suggest here is to approach explainable AI for a problem that we understand really, really well. So we know how multi-agent pathfinding works, we know how to find plans, we understand the plans when they're found. The emphasis here is to somehow convince the human very quickly that the paths are indeed not colliding. There's also a theoretical interest in this plan because it shows a nice connection between multi-agent pathfinding and the problem of finding disjoint paths in graph, which are not usually connected, and they have some interesting interplay between them. I'll mention a bit about this later. It also gives another parameter for evaluating a plan in multi-agent pathfinding, namely the number of segments you need when you decompose a plan, and I'll talk about that soon. All right, so what are the problems we study in this work? The first one is just multi-agent pathfinding in general. This is the problem of finding a plan of non-colliding paths for the agents. This is a traditional problem. We don't add anything to it in this work. Given a plan, the first problem that comes to mind is plan decomposition. So we're given a plan and some parameter m, which represents the number of segments we're allowed to give, the number of frames. And we ask, is there a disjoint decomposition of this plan that has at most m intervals? And if there is, we want to find one. Now, once you think about this plan, you actually see that a much more interesting problem is to find a plan that admits a simple decomposition. So given a multi-agent pathfinding instance without a plan and this parameter m, can we find some plan that admits a disjoint decomposition with at most m intervals? That is, can we find a plan that decomposes well into a small number of segments? That is an easily explainable plan. So what are the results? We call this the first problem planning, the second problem explanation of a plan, and the third problem planning for explanation, or planning with explanation in mind. What results do we have about these problems? Well, multi-agent pathfinding is known to be NP-complete, even for some restricted cases. Interestingly, given a plan, finding a disjoint decomposition can be done in p-time, and in fact it's a very simple greedy algorithm. Just try to add time units until the paths intersect. Once they intersect, stop and start a new segment, and this turns out to be optimal. Now, planning for decomposition, or planning with decomposition in mind, is obviously also NP-complete because it's harder than multi-agent pathfinding in general. Interestingly, it's much harder in a sense, in that even if the number of agents is fixed, it still remains NP-complete. And the reason for that is that it actually forces you to find disjoint paths and graphs, which is also an NP-hard problem for restricted cases. So this is a much harder problem. Right. So a bit more generally, what kind of properties do these explanations admit? So in general, when you look at certificates trying to explain some phenomena or some algorithm, what kind of properties can you reason about? So I suggest a few properties. The first is soundness. If I present you an explanation, you should become convinced that what I'm trying to explain is true. In this case, if I present you a decomposition of a plan, you can become convinced that the agents don't collide. Another property is completeness. Is it true that every plan admits a decomposition? And the last property is simplicity. So the explanation I give should be simple to understand. Now, another interesting aspect of these properties are the intersection regions between them. So things that are sound and complete I will call proofs, because well-behaved systems have sound and complete proof systems. Another property, another intersection zone, is the intersection of soundness and simplicity. So things that are sound and simple I will call explanations. And the reason is that if I present to you this simple piece of data or simple piece of information, it should convince you that what I'm claiming is true. And the intersection between completeness and simplicity I will call diagnostic information, in the sense that it's not necessarily sound. That is, for example, if I try to convince you that something is a guitar, I can present to you 6 strings. Now, every guitar admits this kind of decomposition or this kind of explanation, but it's not true that anything with 6 strings is a guitar. So it's not a sound system, it's just complete. So our explanations are sound and simple, or at least sound. Interestingly, these properties are not just Boolean. You can talk about them quantitatively and look at trade-offs between them. So for example, our decompositions offer a trade-off between simplicity and completeness in the following sense. If I give up simplicity, and in this case, by simplicity, I mean the number of pictures should be small. The number of frames I use should be small. If I give that up and allow any number of frames, then the scheme is complete. I can decompose any plan into each time segment and give out this as an explanation. So it's not simple, but it's definitely complete. On the other hand, if I want simplicity, if I want the number of segments to be small, I have to give up completeness because some plans are not explainable by a small number of pictures. But again, simplicity. So this is an interesting trade-off to look at, and we'll look at it in a second. So let's look at this example here, where the agents, the blue and red agents, try to reach their blue and red targets through this corridor. Now they can't go in this corridor together because they'll collide. The fastest plan is, of course, to send them one after the other, in which case they reach their targets in 8 time steps. The problem with this plan is that the decomposition segments of it are large. So we need 8 decomposition segments, and the reason is that in each time segment, the agents step on each other's paths. So the paths intersect at each time segment. So I need a new frame for each step, so 8 frames. On the other hand, there is another plan that achieves this goal, where we send the blue agent first to complete the target, and then we send the red agent. This plan has two decomposition segments, the first one until the blue reaches the target, and then the second one until the red reaches the target. The problem is, of course, that this plan is much longer. So if I want to explain short plans, I need to give up simplicity because they might require a lot of segments. If I want a small number of segments, I might lose some completeness. I might sacrifice at least the length of a plan, or maybe even the existence of a plan altogether. Right. Now, if we want to implement this in practice, we need to consider this setting in a continuous setting. Now, traditionally, in order to handle a continuous setting, what we do is discretize the dynamics in the environment of the agents, and then plan a discrete setting. This works well in our case, as it does in a lot of multi-agent pathfinding scenarios, but we need to take care of something a bit fine, which is that in order for the discrete decomposition, that is the decomposition we obtain in a discrete setting, in order for this to make sense in the continuous setting, we need to make sure that the agents move in some synchrony, because we need that after each segment, all the agents reach exactly the end of this segment. Otherwise, the paths themselves might intersect. Now, interestingly, if we use a finer discretization, typically a finer discretization may yield better plans. It turns out that even when it doesn't yield a better plan, it might yield a better explanation. So if we look again at this corridor example, suppose this is obtained by some discretization of some environment. And maybe if we use a finer discretization, it will turn out that this corridor is actually wide enough for the agents to pass together. In this case, the fastest plan can also be explained in two frames, in two decomposition segments. So we don't get a quicker plan, but we do get a better explanation for this quicker plan. Right, so to sum up, disjoint decompositions are an explanation scheme for multi-agent pathfinding. And finding a minimal decomposition for a given plan, that is a decomposition with a minimal number of segments for a given plan, is easy. But finding a plan that admits a small decomposition is very hard. And this adapts well to the continuous setting, supposing you've overcome this hardness. Now, for future research, the first thing we want to do is optimize our algorithm. Currently, the algorithms we implemented don't actually take into account the number of decompositions that we want to achieve. So we actually just do multi-agent pathfinding basically and try to find a plan with a small number of decompositions. Another thing to consider is a relationship with the state of the art in multi-agent pathfinding. So one nice approach in multi-agent pathfinding is that if we found a plan for one agent, we use this to define a highway for other agents to take as well. But this behaves really badly for explanations because the paths will now intersect a lot. So how do we combine these two things? Explanations and highways, for example. And another interesting thing is to consider the 3D setting. So if you follow this closely, this explanations make sense theoretically in any dimension, but in practice, if you want to look at a plan and see that the paths are disjoint, it needs to be in 2D, because otherwise paths can be in 3D, but they will look intersecting. So how can we define these things to work in 3D? This turns out to be quite an intricate problem, and we're working on it. Thank you very much.